Oh. Okay, so like I said, today we're only going to talk about the first two topics there, volumes with the disk method around the x-axis, y-axis, and then other axis. So we're going to do one example of each of those, and that's all we're going to do today. So we're only going to get through the first 3 pages of the notes. We'll finish the rest of notes next class, and I do believe that will be our last day of actual taking notes, new notes in calculus. The rest of the time will mean we're going to be reviewing, we're going to be taking tests, we're going to be doing some projects, and then reviewing for your final. Okay? So, full project, just one project. Okay?
Is it worth a lot of points?
So, the disk method, what we talked about the previous classes is we had these cross sections, right? Specifically squares, rectangles, triangles, and semicircles that we found the area of, and then we integrated the area to find the volume, right? Same idea, but now we're going to take this rectangular shape and we are going to rotate it, okay, around the x-axis or around the y-axis to create, if I rotate this one around the x-axis, I get a shape that looks like this. I've got like a cylinder looking thing, okay? So we're taking that 2-dimensional shape and we are rotating it into a 3-dimensional figure. If you remember back from geometry, volume of a cylinder is pi r squared times the height, right? It's the area of the base, which is pi r squared, times however tall my cylinder is, right? Now, when you're talking about integrating those two things, you got 2 pictures here that are pretty nice. When we're doing a horizontal axis, that means rotating around the x-axis like this dx piece, right here is your height, okay? So if I take that, I'm squaring it to find the area, and then this little piece right here, that little dx there is my height, okay? So we're taking this formula of this rectangle and integrating that in order to find the volume around the entire shape, and the pi will just pull out in front. So your formula that you'll need to remember is pi times your integral from a to b of whatever my function is squared, okay? Every single time it'll be the same. The only thing that's going to change is if we're in respect to x or if we're in respect to y. Okay, so I'm going to attempt here to draw what this shape's going to look like. I am not an artist by any means, so if I were to create a rotation about the x-axis here, just to help you visualize, I like to draw that little notation to kind of show you which one you're going to rotate around. This would create the rest of that shape right there, right? See, it's already looking kind of sad. But then think about, these are all cylinders. So you kind of have this 3D dome looking thing, but it's on its side, right? Okay, so this r of x distance, again, this is just your radius of that cylinder. So if I know that distance, the top curve minus the bottom curve, I can plug that in for my r of x piece of my integral, and I can integrate that squared, and that would be my volume that's created for the shape that we have. Okay, the difference of if I rotated this shape around the y-axis, that means I am rotating it this way. This shape would come out here. So I've got kind of a semicircle thing there. And then again, if it was 3D, I would basically have this dome-looking thing where it kind of looks like a little, like one of those little toppers that you put on top of like a cake stand a little bit, you know? Kind of looks like that to me. Okay, so do we see the difference there, rotating about the x-axis versus the y-axis? Great. Visualizing it is the hardest part. If you can visualize it and see where this rectangle piece is, if it's either vertical or if it's horizontal, then you're able to find out what that distance is, okay? All right, looking at this first example here, we're using the disk method. Find the volume of the solid formed by the revolving region of the graph f of x equals the square root of sine of x, and the x-axis from 0 to pi. And then we're going to shade in the region that's being rotated and draw a representative rectangle. So there's a lot of things that we got to do there. First thing is that the curve that's shown is the square root of f of x. So I'm going to label that thing. This is the square root of sine of x. And then it also says that it's bounded by the x-axis as well. So I'm going to go ahead wherever it's, and also where I'm like rotating it, it says we're rotating it about the x-axis. So I'm going to draw a dashed line on the line that we're rotating it around. So we're rotating it around the x-axis. And that's also my boundary line as well. So the shape that we're rotating is going to be this thing in between those two curves. So in between here is what we're going to rotate around the x-axis. Okay, so when I rotate that shape, I've got the same shape on the bottom. And again, these are like cylindrical pieces. So this is a 3D shape that's created. So it's kind of like a weirdly, oddly shaped football, if you kind of think about it like that. It's not quite a sphere, but it like tapers off at 2 points there, okay? Like a puffer fish. Kind of. Okay? When it says to draw a representative rectangle, all that means is it wants you to draw a rectangle so that you know what the top curve is going to be and what the bottom curve is going to be, or what your radius is going to be for that shape. So that radius is this piece that's colored in yellow there. So I'm just going to go from the top curve down to the bottom curve, and I'm just going to kind of create a little rectangle there. This shape is kind of our representative rectangle that we would rotate around to create that cylinder, okay? And to figure out what this distance is, our radius is just our top curve minus our bottom curve. So I've got the square root of sine x minus 0, right? I'm not technically going anywhere else. I'm subtracting that x-axis as my boundary, which just means that my radius is now also the square root of sine of x. Does that make sense? That piece right there colored in black is just the square root of sine of x. Okay? So now our formula, or our volume formula, generically is pi times the integral from a to b of my r of x squared dx function. And r of x there is just my radius that I'm going to plug in. So I've got pi out front, and then I'm integrating this square root of sine of x squared. And then what are my bounds going to be? Where am I starting at for x's, and where am I ending at for x's?
0 and pi.
0 and pi. Start at 0, end at pi. Okay, and then from here we can go ahead and integrate this by hand. Let's do a little simplifying algebra before we integrate. If I square the square root of sine, I end up getting just sine, right? So I've got the volume is pi times the integral from 0 to pi of sine of x dx. And if I integrate sine of x, what do I end up getting? Negative cosine. Very good. So I've got pi times negative cosine of x, and we're going to evaluate that at pi and at 0. Okay. I'm going to go ahead and take the negative pi out front, and I'm just going to evaluate cosine at pi and at 0, so that way I don't make a silly mistake with my negative. So I've got cosine of pi minus cosine of 0. Okay, so then if I evaluate this, cosine at pi is going to be what? What's my x value at pi?
-1.
-1. And then cosine at 0?
1.
+1. So -1 minus 1. If I evaluate that, that gives me a -2 times a negative pi. So 2 pi is my volume of this shape that is created by rotating the square root of sine x about the x-axis. All right, example 2, we are going to integrate with respect to y this time. So we're finding the volume of the solid that's formed by revolving the region that's bounded by the graphs y equals x squared plus 1, x equals 0, y equals 1, y equals 3 in the first quadrant about the y-axis. So take a minute. I want you to sketch all 4 of those curves and lines on your graph before I show you what it should look like, and highlight the region that's bounded by all 4 of those things. And then we'll talk about what to do next. All right, do our graphs look something like this? Hopefully, yes. And then if we are rotating the region in the first quadrant, we're rotating this region here that's bounded by all 4 of those lines, yes? Okay, so we are rotating this about my y-axis. So I'm rotating it around the y-axis, not around the x-axis. So when I'm integrating this, I need my stuff to be in terms of y. So my lower bound, upper bound has to be in terms of y. What I'm integrating has to be in terms of y, not in terms of x, okay? So we are rotating this highlighted region around this y-axis, which we're going to create another dome type shape here. Here's my cylinder, and it's going to look something like this. Okay, it's a dome, but it's sitting on its vertex, okay? Now, when I'm drawing my representative rectangle this time, I'm not going to draw it to the x-axis or like vertically. I'm going to be drawing it horizontal to the y-axis. Okay, so let's do pink here. Okay, so I'm going to go ahead and create my rectangle. This piece right here, I need to figure out what is that distance. But I need to figure out what that distance is in terms of y, not in terms of x. Okay? So I know that my red curve up here is x squared plus 1. So if I know that y equals x squared plus 1, if I integrate that, that's with respect to x, not with respect to y, right? So if I go ahead and solve this for x, then that gives me something in terms of y, but it's the same function, right? So let's go ahead and subtract that 1 over, and then I get y minus 1 equals x squared. So I could take the square root of both of those, and I get x equals plus or minus the square root of y minus 1. Now, if we're talking about this distance right here, that distance, is it going to be the positive or the negative version of the square root of x, or sorry, y minus 1? The positive version, right? So this piece right here, my radius, is going to equal the square root of y minus 1. Okay? Technically, we also would subtract 0, right? Because it's going to the y-axis. But is that minus 0 really going to affect my radius? No. Okay? So I know my radius. I'm taking that radius and I'm going to plug it into my formula with respect to y. So when I'm integrating this, my volume is pi times the integral of a to b of r sub y dy. We're in respect with y this time. Sorry, that's a little cramped there, but same exact formula, but in terms of y instead. So I'm going to have pi times the integral of the square root y minus 1 squared dy. And then where am I starting at for my lower bound in terms of y? Where am I starting at? Yes, we're starting at 1 and we're going up to what? 3. So instead of starting at 1 and going, or sorry, instead of starting at 0 and going to like 1 point, whatever that is, okay, we are doing it with respect to y because we're rotating it about the y-axis. So our bounds are going to be from 1 to 3. Does that make sense? The difference between your vertical, or sorry, your horizontal bounds or your vertical bounds, depending on if you're doing x or y. And then this is something we can integrate by hand as well. So this is going to give me pi times the integral of 1 to 3. And then if I square the square root, that gives me y minus 1. What do I get when I integrate y? I heard someone say it. Y squared over 2. What do I get when I integrate 1? Y. Yeah. So I got y squared over 2 minus y, and then I'm going to evaluate that with my fundamental theorem of calculus at 3 and at 1. So if I plug in 3, a little fraction work here, 3 squared over 2, that gives me 9 halves minus 3. And then I plug in my 1, keeping those parentheses there. That's going to give me 1/2 minus 1. Okay, go ahead and finish simplifying that. Get your common denominators. Keep pi in your answer. Don't plug it in the calculator. Try it by hand. And then I'll give you the final answer to double check yourself. I do agree. Answer should be 2 pi. Okay? They're not always going to be 2 pi. I know the 2 examples that we've done so far are 2 pi. They won't always be 2 pi though. We'll do an example right now that will not be 2 pi. Okay? So last example, then we'll take a little break, and then you guys will have time to work on your homework. Okay? All right. Example 3 here. So we've done one where we rotated about the x-axis. We've done one where we rotate about the y-axis. Now we're going to rotate about something that is not the x or the y-axis. Okay? So we first have to graph what these curves look like. I've got f of x equals 2 minus x squared, g of x equals 1. What does g of x equal 1 look like? Is that a vertical or a horizontal line?
Horizontal?
It is a horizontal line at 1, okay? So I'm going to start out here. I'm going to do that one in red. I'll do this one in blue. Okay, so 2 minus x squared means I'm starting up at 2 and going down 1 over 1 to find my curve. Oops. And then g of x equals 1. I do that one as a dashed line as well because that's also the line that we are going to be rotating around. Okay, so I'm rotating around that blue line. The region that is bounded by the red curve and the blue curve. So that region bounded would be this thing, this thing inside here. That's what I'm rotating. Okay, so if I take that shape and I rotated it around that blue line, I would get another curve that looks something like this. And then again, these are 3D slices that are being created. So again, you kind of have another like football looking shape here that's created with that curve being rotated about the line y equals 1. So when I'm going and drawing in my little rectangle here, my rectangle is going to be drawn in between my top curve and my bottom curve. So it's going to go from that red line to that blue line. That's my little rectangle piece right there. That's the radius of my cylinder. So I need to figure out what does this r value equal.
2 minus x squared minus 1?
Yeah, we got to take my red curve, which is the 2 minus x squared, and then I need to subtract my bottom curve, which is 1. And if I simplify that, that is going to give me just 1 minus x squared. It's always the top curve, and maybe this is a good thing to write down as well. It's always your top curve minus your bottom curve. Okay, so now when we're integrating this, we are integrating it with respect to what? X or Y? X, because I drew my X, or my rectangle. I drew my rectangle vertically, which means I am going to, it's perpendicular to my x-axis, so I'm going to integrate with respect to x as well. So that means I'm going all the way from -1 to +1, okay? There's 2 ways that we can integrate this. We can either go from -1 to +1, or what else could I do? I could do symmetry, right? I could just do this half and then times it by 2, right? Less places for you to make mistakes, so that's what I'm going to show you first, and then I'll also write the non-symmetry version up there. You can choose either one, but I just think you make less mistakes if you do the symmetry version instead, okay? So if we're using symmetry, ooh, that's large. Our volume formula is going to be still r pi times a to b of my function but if we're using symmetry, we're going to start at 0 and go to 1, okay? And then we're going to multiply that by 2. So I'm going from 0 to 1, and I'm multiplying it by 2. And then my radius, my r of x function, I can go ahead and plug in there. That's my 1 minus x squared piece right here. So I'm going to plug this in to my equation. 1 minus x squared squared. And then I can go ahead and integrate this. I would highly recommend to FOIL it first. That way you don't have to do any u substitution or anything like that. So this becomes 2 pi times the integral 0 to 1. If I FOIL this, 1 minus x squared squared, I end up getting 1 minus how many x squareds? 2x squareds. And then I'm left with a plus what? X to the fourth. Okay, if you need to write that out and factor it, go ahead, do that. But I would simplify this first because now this is an easy, we can integrate each of these individually by separate pieces. And then I can go ahead and plug in my 0 and my 1. So I've got 2 pi. What is the integral of 1? X. What is the integral of negative 2x squared? Yep, negative 2 over 3, x to the third. What about x to the fourth? X to the fifth over 5. And then from here, we're going to plug in 1. We're going to plug in 0. I'm just going to leave that 2 pi out in front, and we'll deal with that at the end. So when I plug in 1, I get 1 minus 2/3 plus 1/5. Do I even need to worry about plugging in 0? Nope, because I'm going to get 0. Technically, it's a minus 0, but that doesn't really do anything anyways. Now I got to get a common denominator because this is something we could do without a calculator. What's my common denominator going to be? 15. So I got 15 over 15. 10 over 15. And then 3 over 15. Combine all those together. And how many over 15s am I going to have? 8 15ths. Multiply 8 15ths times 2 pi. That gives me 16 pi over 15. Okay, so that is my volume that is created when I take this shape that's bounded by the red and the blue curve and I rotate it about the line y equals 1. Okay, so all you're doing today is it's going to either go to a line like y equals 1, x equals something, and it's either going to be in respect to x or in respect to y, depending on which one the question is asking you of. Does that kind of make sense? Okay. If you don't understand how to do today's stuff, next class is going to be really tricky. So you really got to make sure you feel good about these problems up here for using the disk method. So that way when we come to class next time and do the washer method, you're ready to go. Okay. Next class, you'll have a quick little mini quiz at the beginning after we go over questions over one problem using disk method and then one problem or one side disk method, one side doing your volume of 3D solids. Okay.